Hey guys, welcome back. So today we're going to be touching on the topic of combustion analysis. Combustion analysis is a method of analysis in the lab that basically involves burning stuff, and then we can get the amount of individual elements that was produced as a result of that combustion. And we can use those mole ratios that say if we know that it produced 2 moles of carbon and 4 moles of hydrogen, we can use that to determine empirical and molecular formulas. The molecular formulas we will obviously need a little bit more information of, but we can use it to determine empirical formulas. Um, it's not really it's not really much conceptually to learn. Um, we could express percentage. So you could also see this described as percent composition by mass. So there's really not much more to it besides you need to know what it is and how to do the problem. So with that being said, let's show you how to do a problem. Um, So let me try and find the problem I was looking for here. Yes, it was this one. So let me zoom in a little bit. For zoom in a little bit. Try that now if you want, and come back for the solution, the one that I've highlighted. All right. So I assume you're back. Let's move that aside and let's sort of get our bearings here. The first thing I like to do is, if we're not given the molecular mass of the formula, let's just say our sample mass was 100 grams. Now, this is more or less arbitrary. Um, Actually, you know what? We are given the mass of the sample. We are given the molar mass of the sample. So let's use that. Let's say we had a mole of compound, which we know is 92 grams. And we know of that 92 grams, by mass, 30.4% of it equals nitrogen. And the other, what is that? 69.6% of that is oxygen, since we know that there's only nitrogen and oxygen in this compound. So let's take 30% of 92.9 grams, and that would be the mass of nitrogen in the sample. So let's do that. So 92 grams times. So what I like to do is generally I like to separate each element out. So I work out for N in one row, I work out for O in another row. So so we know that of the 92 grams, we know that 30.4% of that was nitrogen, which yields, uh, if I pull out a calculator, so let's pull out a calculator here. So we do 92 times 0 times 30.4 over 100, because I forgot to do it in decimals. We know that 27.968 grams of that was nitrogen, and similarly we know that 69.66% of that was oxygen, which yields, so 92 times 0.696, we know that 64 grams, about 64 point something point point 0.032 grams of that was oxygen. Now, I'm going to do a bit of mental math here. Now we convert it to moles. So using our molar masses, I happen to know that the molar mass of nitrogen is 14.007 grams, 1 mole, and this should be 15.9994 grams. So let's do that. 27.968 over 14.007 yields 1.996. You don't have to be anal about sig figs. Oops, wrong. You don't have to be particularly anal about sig figs. I opened the wrong window there. What was I going to open? Oh yes, the calculator. Yeah, my bad. I was going to open the calculator up. You don't have to be particularly anal about sig figs, just as long as you have enough of them. So 64.032 over 15.4, which yields 4.002. And then the rule of thumb here is that you divide. You divide by the smallest number. If you don't know, you either divide. The rule is you divide by the smallest number. However, it's pretty clear to see that that's pretty close to 2, so let's call it 2, and that's pretty close to 4, so let's call that 4. However, if it was a little bit less clear, divide through by the smallest number and you'll get something that's a bit more clear. The idea here is that you want to either round to a simple fraction. So the idea here is that you want to round to a simple fraction. And then we can clearly see here that there's 2 moles of nitrogen for every 4 moles of oxygen, and the molecular formula should probably be N2O4. So that would probably make sense, and that is in fact the answer. Now it also asks for the empirical formula, which is NO2. However, if we didn't know the molecular mass of the compound, let's change things up here. Say we didn't know the molecular mass of the compound. Or say that we didn't know it initially. So part A says what's the empirical formula of the compound. So let's work at it a little bit differently. So what you can do is take a random mass. So I'm going to make my life easy, and let's say our sample mass analyzed was 100 gram. So since we know that 30.4% of that 30.4% of that mass is nitrogen, and 69.6% of that mass was oxygen, we know we can. I intentionally chose 100 grams here because the math was easy, but you could have chosen different numbers and it would have worked just fine. So again, separating our elements here, we get 30.4 grams and 69.6 grams. The reason I chose 100 again, it was sort of an arbitrary choice, but I chose 100 because, it was played nicely into the percentages. And that would have, so then that's the mass of the thing, that's the mass of nitrogen in the compound. And we do this sort of same process again, where so 14.007 grams, 1 mole over 14.007 grams. And then that should yield, like, if I pull a calculator out, should always have this thing at the ready. So 30.4 over 14.007, which yields about 2.17 something. It doesn't really matter. And similarly, if I do 69.6 divided by 15.9994, here it's a little bit less obvious, so 4.35. Here I can't see any discernible ratio, so let's divide through by 2.17, which should yield no, I should pull that back up, divided by 1 in this case, then divide that by 2.17, which should yield 2.0041. And now it's pretty easy to see that, okay, this is clearly 2, this is 1, and then we have NO2 is the empirical formula. And then now it said in part B, the molar mass was 92 grams. What's the molecular formula? Now, the easy way to do this is take the molecular mass of this empirical formula, so 14 plus 2, 16. I'm just rounding off numbers here for the sake of neatness, I guess. And this should yield a molar mass of about, so 32 and 14 makes 46. And then we can divide 92 by 46. So the mass of the molecular formula over the mass of the empirical formula, which yields us 2. So what this tells us here is that 2 empirical formulas make up the molecular formula. So we have 2 of these, and we would get N2O4, the same answer we got the other way doing it. So yeah, that's really it. Thank you so much for watching. Don't forget to like and subscribe.